They do look a bit just like bouncing balls, I gotta say, and not snow. It makes me think that like I want to add just more chaotic wind forces in here. So maybe we'll say like there's going to be a point that just pushes them away from it. Hello, what's up everybody? Welcome back to Peaceful Coding Tutorials. And today we're going to look at how we can make a snow effect in the browser. And so we're going to be looking at how we can draw some particle animations. And to do this, we're going to be using this library called Three.Js. 3JS is an awesome library when it comes to doing high performance 3D or 2D rendering in the browser. It's essentially a wrapper around WebGL, which is a framework for rendering things in the browser. And so let's go ahead and jump right into it. So the kind of key idea with what we're going to be doing today is we're going to be rendering a ton of different meshes, where a mesh is kind of a single object in Three.js. And ordinarily, we would have some kind of performance issues if we tried to render thousands of meshes in the browser. However, we have access to this concept in Three.js known as an instanced mesh, and this is going to allow us to render a whole bunch of the same thing over and over again without having any kind of performance problems. So in our case, we'll use one particle as our sort of single mesh, and then we'll clone this single particle all over the place in order to make this snow effect. So it should be pretty cool. I have not tried this before, so let's see how this goes. The other thing to note is we're going to be using this points material Three.js concept for the kind of material in Three.js that each snowflake or each particle uses. All right, so let's go ahead and just jump into it. On the right, I've got my command line open to my Peaceful Coding Tutorials folder, and let's go ahead and make a new folder in here called snow or particles or something like that. I'll just call this snow, and let's open this up in our VS Code window, and I'll go ahead and make this interface much bigger. Okay, let's go one less. All right, perfect. So let's start off as we would with any more or less dependency-free web project. In this case, we are going to be using Three.js, but other than that, we won't use any dependencies. And so we'll just start off by making an HTML file. I'll type the exclamation mark to get the starter HTML boilerplate code. You can type snow in here. And let's also make an empty JavaScript file, and we'll import this into our HTML file here. All right, perfect. The other thing we're going to need is we're going to need the Three.js package code. And so let's go ahead and see if we can bring that in. So they're telling us that, hey, if we're using some kind of bundling system, we can use the import statement. There should be another option in here as well, import from a CDN. That's what we'll do in this example. And I haven't actually tried this exact syntax, but let's try it out. We'll just pop that in our index.html. And from here, we're going to want to see if we can just get kind of like a starter scene working at all. And that'll let us know that things are kind of actually working. And so let's go ahead and we'll try this kind of starter example real quick just to make sure everything's working. So we're not going to need to do this because we're not using kind of the bundlers I mentioned. This three variable is actually going to be just defined sort of globally in our browser because we've imported it above our main script with this other script up here. And let's go ahead and just see if we get errors in the browser when we do this. And so we can open this index.html file up. Kind of the best way to do this is with Live Server. This is a plugin for VS Code. So if you just do install extensions and look for Live Server, I definitely recommend installing this thing. It pretty much just gives you a live reloading way to serve HTML and other static front-end content. And so if we right-click, open with Live Server, and let me make this a little bit smaller, we can see that we're able to open up this index.html file that we just made. And we are having some issues. We can see, okay, 3 is not defined. And so let's see, do we possibly need this? The crazy thing about web development is it is always evolving, and okay, yeah, so we're not going to be able to import this. and thus the syntax does change. So let's look back at the documentation. I'll actually give it a closer read this time. As far as installing this thing from a CDN. Very interesting. Okay, so they say put this thing inside the head of the document. Let's try that. And we'll open this thing back up and see if we're getting errors here still. 3 is not defined. Let's try this. Okay, we got a different error. This could be progress. And we may need to replace, okay, version with the version of 3 we want, like this. Okay, so let's go ahead and do that. Okay, and it turns out reading the documentation is pretty helpful. Looks like we still have some kind of issue. Oh, you know what? I left the kind of greater than and less than signs. Oh my goodness, and look at that. Okay, so we've got a working situation here. So we've got 3 installed properly, and now I think it's just a matter of doing what we want to do with 3. So it's probably a good idea to carry out with this starter example where we just kind of go through their getting started information and add this cube that they recommend and see if we can get the cube to show up on the screen. And that'll give us kind of like good certainty that everything is working. And there we go. Okay, we just randomly copy and pasted code until we got there. But here we are, we've got a cube, and that's perfect. So we kind of copy and pasted in the starter example for Three.Js, and looks like it's working. The other thing I'm going to do is I'm going to add some styles to get rid of the margin on the body element of our HTML here, which is just sort of annoyingly giving us a little bit of a scroll element. And so we could just do this right on the body tag. And so we'll say margin is going to be equal to 0. All right, great. So this is looking good. Let's go ahead and proceed with our snow effect. And what we'll do is we'll start with a single snowflake, and from there we will add more. Okay, so we're going to need some of this boilerplate 3 code. The stuff we're not going to need is the stuff related to creating a cube. And so that's going to be kind of this stuff here. Let's just calm this out for now, and we'll come back to it. Above here, we're just kind of setting up the scene for Three.Js, and we're setting up the Three.Js renderer. This is just a bunch of boilerplate stuff that needs to be created in order to make 3 work. And then from here, we're going to go ahead and say, create this animation loop, and every time the browser is available to render an animation frame, go ahead and call this function, which in turn will call the Three.Js renderer and say, hey, render this scene that we've set up with all of our objects and whatnot in it. Our meshes, and then also use this camera for the scene to know where we should render. And super small, I kind of generally prefer using arrow functions, so I'm just going to switch this around. It doesn't really matter, to be honest. Okay, there we go. Cool. All right, so let's go ahead and add a snowflake. And so what we'll do is we just want so pretty much the basics of Three.Js is that every mesh, which is a thing that gets rendered in the scene, like the cube we were looking at, and so if we uncomment this out, we can see the cube again. Every mesh consists of a geometry which defines kind of the vertices and edges and faces of the thing that's being rendered. And additionally, there's a material. And so we can see we have a green material here, and it's just the mesh basic material. There's other materials that allow you to add shadows to elements and all kinds of crazy stuff. And we're going to be using the super simple points material in our example. And so let me just navigate through these Three.Js docs to look at that points material. And there we go. Let's actually try just adding the points material to the cube to start with to see if this is working. And so I'll just copy the line in the documentation here that defines the points material, plop it in here. Let's also minimize this thing so we have more screen real estate to work with. And it's got some gray color or something like that. And let's see how that works. Okay, interesting. So the points material in this example actually made this a solid thing still. I was actually kind of expecting that we would see it just to essentially render a point at each vertex of our cube, but that's all good. Let's read the points material documentation a little bit more and see if there's any other properties that we need to pass into this thing. So these are the available properties. Looks like size attenuation is an option. Size is an option. Defines the size of the points in pixels. Definitely interesting that this rendered the full thing. That is totally fine though. So let's go ahead and just proceed with what we were planning on doing, which is we're going to make what's called a buffer geometry, which is like a super custom geometry that lets you set the exact points. So a box is kind of like you pass it in width, height, length, and that's going to just make a box. But for buffer geometry, we're actually going to pass those points in directly. And we could, look through the documentation for how we actually do this, but let's actually just go ahead and type into ChatGPT, how do we make a buffer geometry in Three.Js with 1 point? And ChatGPT should spit out some code. Create a buffer geometry instance. It's going to be something like geometry equals new buffer geometry. And then, okay, great. So I'll make this a little bit bigger so you guys can see. But essentially, it's saying that we just need to create some positions, which is going to feed into this buffer geometry. Float 32 buffer attribute, and oops, I gotta hit myself. So positions is going to be a float 32 array. This will define our coordinates, and let's just say that we've got a single point at 0, 0, 0 right now. And from here, we'll define the position attribute of our buffer geometry. This is just what 3 wants us to do. And we'll say, okay, pass that in, and there's going to be 3 values per vertex. Okay, and then finally, we're going to finish off creating this single point buffer geometry by calling the set attribute of the geometry and setting the position attribute equal to this position attribute variable that we made. Okay, great. So let's see what this looks like. And it looks like nothing. That's totally fine. And I think this is where we may need to adjust our points material in order to view the actual vertex here. So let's go ahead and do some Googling here. Or we could just ask ChatGPT. It's always worth a shot. Sometimes it'll lie to you, but sometimes it has good information. So how do we render that single point of the buffer geometry as a dot? As far as using ChatGPT goes, it's hit or miss. It's very good on well-documented things I've found, but if you're trying to do something that people haven't really done before, it's going to have a much harder time. The other thing is, if you do pay the $20 per month and get the ChatGPT 4, it's definitely a bit better than 3.5 in terms of just its accuracy and its ability to give you good explanations. But yeah, we are seeing that it's also recommending that we use the points material concept that we are using here. Let's see. Okay, so they did pass in a size property, or ChatGPT did rather. So let's actually go ahead and try that and see if that is what we need. The other thing is it is possible that our camera is not sort of looking at the point, which is always a little bit of a tricky thing with Three.Js. Oh, well, should be fine that we're calling this a cube actually. Oh, you know what? Here it is. Okay, so instead of making a mesh, we need to actually make a points. That's kind of one thing that I did forget about. The other weird thing is we're still calling this a cube. Let's call this points or mesh or something like that. What the heck? Okay, so we are getting a big old square. This actually looks a lot like a cube, but I believe that the particles that are rendered are just also squares. And so here we go. We're seeing our single particle, and it's really big, but we can adjust the size property, and there we go. We've got one particle, one particle. Let's also go ahead and change the color to be white to be, more like our snowflake, and we'll just tweak the size of this until we've got something that looks good to us. Okay, so there we go. We've got one snowflake. From here, what we're going to want to do is we're going to want to adjust this thing's position somehow. And the idea I had for this is that we'd add some kind of gravity where the snowflake would always be falling down, and then we'd add some kind of wind forces around that would adjust the position of our stuff as time goes on. And so let's actually, aside from all this Three.Js code, let's add some code that stores the position of our snowflake and adjusts it over time. And so we'll go ahead and it's a toss-up as to where we store this stuff. But let's go ahead and we also may want to make this an instance mesh before we begin, so that we're kind of all set up to add more of these things when the time comes. So let's actually do that, and we'll say that, okay, we are going to, well, the one hesitation I have is the fact that we are using this points thing here. Is there like an instance points? All right, did some research, and I think we're going to do a new approach as to how we do this. So pretty much what I decided is that let's continue to leverage the instanced mesh approach in which we render a bunch of meshes. But to do this, we're not going to be able to use the points object or the points material. And so I've got a new example set up here in which we're using the plane geometry material. This is pretty much a square. So if we look at the plane geometry in the documentation, you can see that this will just render a square. And we've got it set up with this mesh basic material with a white color, and it's just rendering the front side of the mesh, and that'll kind of help performance sake. So we can see, okay, here's our square. We can also go ahead and say, let's store our particle size in a variable up at the top, where we'll say, okay, this is particle size 1, and that'll make a square with width height both equal to 1. Okay, perfect. So let's go ahead and tune our particle size now to be a smaller particle, and let's go ahead and proceed with the rest of this example. Okay, so for the instance mesh object, we pass in the plane geometry, we pass in our mesh basic material, and we pass the number of these things we want to be rendered. From here, we're going to apply transformations to each mesh in our instance mesh, kind of each version of it, in order to put our various snowflakes in various different positions. So let's just start with a single position, and we will write our code in such a way that it'll work well once there are multiple positions, though. And so we'll say, okay, let's go ahead and create an array of positions, and we'll just do x and y. So we'll say that x is going to start at 0, y is going to start at 0. And let's also go ahead and add a velocity for this thing. So we'll say that this snowflake has some velocity, and we'll say that that is also 0 when this thing starts out. So from here, let's apply some kind of force to this snowflake as it animates, and we can say that every frame that goes by, this thing will have some gravity applied to it. So we'll say that gravity acceleration is going to equal, let's start with 0.1 or something like that. So from here, let's go ahead and say that, and let's also make this velocities, not velocity. Every time our animation frame occurs, we're going to go ahead and loop through all of our velocities and update them so that velocity, well, let's first make a loop. So for velocity of velocities, let's go ahead and say that velocities or velocity dot y, and we'll go ahead and let's say that a negative velocity means that it's going down, a negative y velocity that is. So we'll say that subtract the gravity acceleration from velocity.y. Perfect. Let's also go ahead and update our snowflake positions every iteration of our animation frame loop. So say for position of positions, go ahead and adjust the Y position and the X position by the current velocity. So velocity, oh, you know what? It's going to be actually a bit better to do this in a single loop. So we'll use our good old for I equals 0, I is less than positions.length, I plus plus. Maybe we also abstract our number of snowflakes into a variable up here. We'll call it num particles in case we want to represent some other kind of particles. And we'll say 1 for now. We're also going to want to use that variable up here. So let's just put all this stuff up here. And sometimes I put my constants in this sort of uppercase style. Let's just kind of be consistent with the rest of the stuff we're doing here and make it lowercase. And then I'll also update the place in which it's used. Okay, so this number of instance meshes that we're making should equal our num particles. And we need to finish this code here. That's why we're getting errors everywhere. So we'll say that, okay, iterate through each of our snowflakes, and we'll substitute positions.length for num particles. And then we'll get the position of that snowflake, which is going to be positions index.I, and we'll get the velocity of that snowflake. And then we'll proceed with updating the velocities of the snowflake and updating the positions, both x and y, and we'll delete this stuff down here. Okay, so position.x is going to get velocity.x added to it, and then same thing for y. And we'll update this, position.y. Okay, that's great. So nothing's actually happening yet, and the reason for that is we haven't actually told our Three.Js instanced mesh to be placed at this new coordinate. So the other thing we're going to need to do is we're going to need to tell our instanced mesh to apply a transformation to the particle geometry. So let's look at instanced mesh and look at the docs for that on how we might do that. Instanced mesh, and there is a method in here somewhere. Let me make this a little bit bigger. Set matrix at. It might be kind of behind the camera. Hold on. Okay, so set matrix at is a method we can call on our instance mesh, which is going to take in the index of the particle that we want to adjust, and it's also going to take in a 4x4 transformation matrix. And we can use that 4x4 transformation matrix. We can create just a simple translation from our position here. So let's do that, and the question is, okay, how do we actually take our position.x and position.y and turn that into a four-dimensional matrix? And there should be a pretty easy way to do that, where we can say that, well, let's just ask ChatGPT. How do we turn a 2D translation into a 4D transformation matrix in Three.Js? All right, let's get to the code, buddy. Oh, what is this? No. Give us JavaScript, not... Oh, okay. So it's pretty simple. We just put the X here in the matrix and the Y there, and the rest is, I think, the identity matrix. But I was kind of hoping for more of just a easy method we could use. I think what we may do is we may make a instance of a matrix 4, and then I think we are just going to do like a dot translate or something like that. Okay, so the most common use of 4x4 matrix in 3D computer graphics is a transformation matrix, blah, blah, blah. Okay, this allows a vector 3 representing a point in 3D space to undergo transformations. This is known as applying the matrix to the vector. Great. Okay, so what's, set from matrix position. That's not quite what we want. We want I mean, we could just plug in these numbers at the end of the day, but make translation. Sets this matrix as a translation transform from a vector v or numbers x, y, and z. Great. Okay, that is exactly what we want. So let's create a transformation matrix for each particle, and maybe what we'll do is we'll actually initialize these positions with a loop, so that when we go to add more particles, this is nice and easy. So we'll say that let's loop through num particles, and each time we do, we'll add a new initial value here. And the reason for that is I'm going to add a matrices array here, and we're going to eventually have to repeat ourselves if we don't do this, so this is probably a good idea. Okay, so position, velocity, very good. And you know what? I'm kind of thinking that we actually just store our... I'm trying to figure out what the most efficient way to do all this is, because we probably don't want to make a new matrix for every particle every time we render a frame. So ideally, I think we just have one matrix that we're modifying. So look back at make translation. Yeah, I think maybe we will just use this as our sort of position value, the matrix itself, and then we'll just say that every time we iterate, add x here or add the x velocity to this, which represents the x position, and add the y velocity to this, which represents the y position. So the question is, oh, set position. Ah, nice. Okay, I think this is actually exactly what we want. This is very nice. Okay, so this is going to be easier than make translation or whatever. And I take back what I said. We're going to continue to store our position in our position thing here, and we'll just call dot set position on our matrix each time. Okay, so let's proceed. Constant matrix, and let's actually just say that position stop push. One of these things, velocity stop push. Matrices dot push. New matrix for, and yes, this will create the identity matrix. Okay. Great, so we've got our stuff set up, and so just to circle back to what we're actually trying to do here, we're trying to render our mesh at the position. To do that, we're going to use this transformation matrix, which is how instance mesh requires us to do so. And from here, we'll also go ahead and make it so that in this loop, after we adjust the position of this thing, we set the particles transformation matrix to reflect that it has that position. So we'll say that matrix is matrices index at I and matrix dot set position xyz. And we don't have a z component. That's fine. We'll just use 0 for z. X is going to be position dot x. Y is going to be position dot y. Z will just be 0. Okay, so far so good. So let's see if we actually have any movement here now. And we don't. Let's go ahead and add a log, make sure that this loop is occurring. Yes, it is. And, oh, I think the thing is we're still not tying this matrix to our instance mesh anyway. So the final thing we need to do here is we need to go to our instance mesh and say set matrix at some mesh's index to the matrix. And I'm curious if we need to do this every iteration of the loop or just beforehand? Let's initially try every iteration, and we'll make a note that says, do we need to do this every loop iteration? And the only advantage to not doing it every loop iteration is we might get some performance improvements that way. So let's go ahead and say instanced mesh, or whatever, we're just calling this thing mesh dot set matrix at, and it's going to be index I, it's going to be equal to matrix. Okay. Nothing. So render.render, that all looks good. That all looks good. So maybe we want to look at the matrix and see if the matrix is actually getting updated. I mean, there's a variety of things that could be going wrong right now, but let's start here. So we'll say, is this matrix being updated as time goes on? And it doesn't. Oh, actually, it does look like it is. Oh, the other thing is it's possible that Y is into the screen in this example and Z is up and down. Let's see if that is the case, and we'll just go ahead and substitute. We'll swap these two. No, doesn't look like that is the problem here. I'm curious to also adjust X maybe. The other thing we could do is, well, it's interesting that we see this thing here. It's almost like we are not re-rendering at the end of the day, but I think we are. Ah, okay, here we go. Make sure you set instance matrix.needs update to true after updating the matrices. Gotcha. Okay, so I think we're forgetting to do that. So we'll say mesh.needs update equals true. Okie dokie. Nothing, come on. So sometimes, you've got multiple problems, and that is okay. We'll get through that. So now I'm like, maybe it was this XY or YZ switch was the problem. Nope, that's good. Mesh.needs update. Let's go back here. Sets the local transformation matrix to the defined instance. Make sure you set instance matrix.needs update to true after updating all the matrices. Gotcha. Okay, and it looks like we're following that syntax to a T, so that's great. Oh, instance matrix needs update. Oops, where am I? Hold on, where we go? What the? Oh, dot instance matrix dot needs update. Okay, so I think I actually butchered this syntax here. Dot instance matrix dot needs update. Holy, okay. You can actually see it's going down very fast. So let's turn down gravity. Thank goodness we've got something working. And you can see it's still super fast. So oh, look at that. We got a particle. Okay, so this is just like absurdly. The other weird thing about what the setup we've got right now is request animation frame is going to be a faster time period on faster computers and a slower time period on slower computers. So ideally what we should do is we should be recording the time in between frames and using that time difference to adjust how fast everything's happening in the game, but I just don't really feel like doing that. So let's just stick with how we're doing it for now. And if we ever wanted to adjust that, we can just keep in mind that we can. The other thing we might want to do is maybe we just zoom out the camera a fair amount, and that makes everything appear to happen a little slower because we are more zoomed out. And that might allow us to use kind of more reasonable values here. And let's also up our particle size to like 1 or something. Yeah, I think that's nice. Okay, great. So the other thing we might want to do is like let's add some interesting forces in to our interesting like wind forces to our scene here. And so we'll say like let's put like maybe one. Well, let's make it so that when the particle drops down to a certain amount, there's a strong upward draft that pushes it back up. And so we can add some rules around that. So let's like make functions for each of the sort of like wind rules we're going to apply or the force rules. So we'll say like apply gravity will be one thing, which we'll move this into. And so we'll say, okay, um, to apply gravity to a force, it's going to, or to a velocity, it's going to look like this. And things are still working the same, that's great. And let's also say apply upward wind. And we're going to need the position for this because we'll say that if the particle is low enough, then it should get pushed back up. And we're also going to want like an upward wind force. Maybe we move our gravity force and our wind force kind of variables closer to each other. I just lost my gravity. There it is, gravity acceleration. We call this gravity force. I don't know. I'm not really an engineer. But let's call this upward. Actually, force is way easier to type, so let's just do that. Upward wind force, and we'll make this much stronger. So this is 100 times as strong as our gravity force, and we'll say that if the position of the particle, and the question is, okay, is it going up or down right now? I think it's going down. So if it's less than, it's hard to know, what is the bottom of our screen really? Let's just guess that it's like 10. So if it's less than 10, go ahead and velocity dot y gets the upward wind force added to it. Upward wind force. Let's see what this looks like. Okay, 10 must be really low. So let's try 1 if the y position is less than 1. Oh, and we forgot to call this function completely, so let's actually do that first. We'll say, okay, we're going to apply all the forces here. Upward wind force, we said that this one's going to require position and velocity. Hold it. Okay, so it just immediately went up, so I think we need to make this like 100 maybe? If the position is less than 100, or less than, right, it's going down, so maybe we need to say less than like -1 or -10 or something. Yeah, so let's say -10, and then let's make this stronger. Okay, it just like bounced, but that's kind of cool. Let's make this lower, and let's make the force a little bit chiller. Okay, it's just off the screen. So let's go with -50. Maybe that's the bottom of the screen or so. Okay, that's cool. I'm just going to tweak these numbers a little bit, just to something that seems kind of nice. That's a little too powerful. Okay, and let's get rid of the console log. So this is looking great. I think the other thing we're going to want is we're going to want some like swirling side forces. And so the other question is like, how do we make this not just look like a bouncing ball and more like a wind effect? But we'll just think about that and keep experimenting with some stuff. Maybe we reduce the upward force a little bit. Oh, that's cooler. I like that. Okay, so let's also yeah, we'll add like a couple side forces. So let's also give this thing, so we'll say that there's like always just like a bit of a rightward force, a force going left to right. And then let's say that near the right edge, there's a strong leftward force that'll push it back. So we'll say that the rightward, well, let's just call it the right force, right wind force is equal, and honestly, this is going to look very similar to the gravity and upward force, so let's just copy and paste. And instead of gravity here, we're going to be using right force, apply, call this right wind at least, apply right wind force, and then instead of upward wind, we'll go left. Okay, and then instead of the y velocity, we're going to use the x velocity here. Okay, then let's actually call these things, and I'm surely I've messed up at least one variable name there, but this all looks pretty good. And maybe we'll adjust the values. Let's just have these forces to at least just make it a little different from our gravity stuff. And I'm just kind of tweaking these randomly. But yeah, that looks good. So let's call these functions. Okay. Cool. Okay, so I did it backwards, but it doesn't really matter. This is still cool. Ooh, this is looking more like wind. Um, so maybe the other thing we do is we give each of these particles a unique weight that makes them sort of like be affected by these forces differently. And we'll say that a heavier particle is less affected by these forces. Oh, it's already very cool. So let's add some particle weights. And I'm kind of getting ahead of myself because I haven't even made multiple particles. So let's actually start there. So we'll add multiple particles. And right now they're just all going to be on top of each other. So let's add some sort of random starting positions that they have. And we'll say that their starting position is not just going to be 0, but let's say that it's going to be between like -20 and +20. And so we'll say, position X is going to be math.random. That gives us a random number between 0 and 1. So we'll say multiply this by the range, which is 40, and then subtract 20 from it, which gives us something between -20 and 20. And then let's just do the exact same thing for the Y. And then we'll sub this out for position X and position Y. Ooh, cool. Okay, so it's still not that interesting because, well, it's actually kind of cool. How many of these can we do? Can we do like 500? Ooh, cool. Whoa. Cool, 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 cool. Okay, so it's still a bit like it doesn't quite look like wind yet. And I think there's a couple of reasons for this. One, yeah, all of our particles have the exact same properties, which makes them move a little bit too statically. And then the other thing is you can see it's got this square shape to it, which I think is due to us just kind of making a hard force on the left instead of making it different. But let's just try adding weights to each of these things and seeing how that affects our our visualization. We could also add sizes to each of these so they're not all the exact same size. So right now they are all size 1, but and maybe weight and size is like the same thing for us. That would kind of make sense if a bigger particle weighed more. So we'll say that sizes is going to be an array, and right now they're all 1. Let's say that they can be from 0.1 to 2, and so constant size is going to be, calculate a random number between 0 and 1, and then our range is approximately 2, we said, so let's multiply this by 2, and then add 0.1. So that's actually going to be between 0.1 and 2.1, which is, that's fine. Okay, and then we also want to actually, oh, you know what? Okay, so we can't, what the, okay, where's particle size defined? Okay, here it is. So we'll put a 1 back in there. So what we need to do is we actually need to change the size of these things through our matrix. And so in addition to our matrix allowing us to set the position, this transformation matrix is very cool in that we're going to be able to set the position, the scale, the rotation of our mesh with that transformation matrix. And so let's look at this thing and we'll look to see where set or scale is. So I think we're looking at the matrix 4 docs. Let's see. Make scale. I think that's what we want. Set this matrix as a scale transform. Great. Okay, so when we make this new matrix, we're not just going to, we'll say, we're not just going to make the identity matrix now, but we're also going to make a scale matrix. Matrix dot make scale, and then we pass in the x, y, and z scale. Like, is there any other way to do this? Like just a dot scale? Oh, dot scale consumes, multiplies the columns of this matrix by the vector v. We just want like a scale by a constant value, but maybe that is not quite how this works. Set from matrix scale. Add scale. Okay, let's go back to plan A here. Dot make scale, and we'll say that size, size, size. We can also give these things like a different x and a y, which could be kind of interesting. Okay, particle size still not defined. Where is that needed? Oh, I see. Okay, so they look like they're all the exact same size. Interestingly. Oh, you know what? It's because we're pushing a brand new identity matrix here instead of the matrix that we spent that time making. Okay, we can see that they're actually different sizes now. That is pretty cool. We also might want to just give them like some random kind of velocity. Like sizes is not used. How's that possible? Oh, we just don't even need it. Except that we do need it because we need it for the weight later on. So push size. Okay, now let's make it so that the small particles are affected more than the big particles. Let's also go ahead and just like square this value, which I think should just make these things a little smaller in general. Nope, that didn't necessarily make them smaller. So maybe we like square root this or something like that. That's square. Cool, that's cool. They're a bit smaller now. That's really nice. That's really nice. But let's actually make these things affected by the weight. So each particle is a size in our updating loop here. Oh, we also did want to check, do we need to update this matrix every instance of the loop? And so let's try avoiding that. And in order to do that, we're going to try putting this code here for let I equals 0, less than num particles, I plus plus, and we'll say that, hey, can we just set this, oops, I messed it up, matrix, so yeah, let's see if this works. Nope, it doesn't work, that's fine. Okay, put it back where it was. So pretty much, I was experimenting to see if we could get a performance enhancement. I mean, not that we really need it yet, but just wanted to check. So we can get rid of this to-do statement. We did confirm that that is needed. Okay, so right, let's make these things affected by the weight. So in addition to the velocity, I'm going to pass in the size property each iteration of this loop. So let's get each thing's size, pass it in, and we'll just pass it in as another parameter to each of these functions. We could probably also go through each of these functions and, I mean, there's actually not that much shared code. This is fine. Okay, so size, and we'll just say that, you know, each force gets multiplied or divided by the size. So that, oh, that's looking good already. Okay, so let's carry this out and we'll just divide each force by the size. This is cool. That is really nice. Oh my goodness. Okay, so it doesn't quite look like snow still. I feel like I want the particles smaller on average too. So let's actually just adjust. Well, we can also just like, do we like the speed is the other question. Is it just the size? Oops, I messed something up. I mean, the speed is a little weird. The whole thing is a little too predictable still. I wonder if we should give these things some random initial velocities. And I'm not exactly sure like what range our velocities are really even in right now. So let's just go ahead and check. So we'll just log out the velocities to see kind of like what ballpark range. Okay, these things are like 0.05 or so in either direction, or like zero point 0.1 even. Yeah, let's give them like a -1 to 0.1 random initial velocity. So velocity x equals math.random. This is 0 to 1, and then our range is 0.2, and then our starting point is negative 0.1. So that should be good. I'll just add the parentheses to make this as clear as possible. And let's do the same thing for y. and then we'll plug in velocity x and velocity y here. Okay, so that's pretty sweet. Let's also up our particle count. Can we do 2K? Ooh. Okay, and then let's say that like base particle size or something is, it's currently 1, so we'll just refactor here, base particle size. And then let's make that just smaller. That is cool. I feel like I still want them smaller. That's just like dust. They do look a bit just like bouncing balls, I gotta say, and not snow. It makes me think that like I want to add just more chaotic wind forces in here. So maybe we'll say like there's going to be a point that just pushes them away from it. So let's make a point force, and I'm thinking maybe we just put it right in the. So many options. So many options. Oh, we could have a moving point. That would be really cool. Let's do that. So let's have a point that just like bounces around randomly. Wow, this is getting really crazy. Maybe we'll just have a point that kind of moves, just oscillates. Well, let's just start with a static point. And so we'll say apply point force. And pretty much what I'm thinking here to actually explain myself a bit better is that we'll have a point that'll push all the particles away from it, just to try to add some more kind of chaotic wind-like elements to this. Because right now it looks just a bit like bouncing balls. So apply point force, and I bet if we had multiple of these, that could be cool as well. And we are going to be both the position and velocity and the size. And I've broken it because I have this random const. Let's get rid of that so we can watch our fun particles. Oh, what's going on? Oh, apply point force doesn't exist yet. Apply point force. Okay, there we go. I like being able to watch this as we code. Okay, so let's just put it at 0, 0. And we'll say that for each particle, let's calculate the distance it is to the point force, and then apply a force to it with a strength that is equal to that distance, where the smaller the distance, the higher the strength, and it'll just get pushed away from the point. Okay, so position, velocity, size, this is all of the particle, and then as for where our point force is, we'll say point force location is equal to, or maybe we'll use position to be more consistent with our previous terminology. And let's go ahead and say that, okay, first we'll calculate the distance, or maybe we just like use this sweet, I know there's great like vector classes in Three.Js. So let's say, okay, so vector, we'll use this to say that x is going to be, let's go position, position dot x minus point force position dot x, and or maybe we'll do like 1 over this. So this will be like a force. This will be nice and chaotic, I think. So let's just go ahead and say that the y force is equal to, or this is going to be x force actually. This is the x force. We're not going to use this vector thing. I'm just kind of rethinking it. I mean, we definitely could, and maybe we'd get more predictable physics, but I kind of just want to add some chaos to this thing without thinking too hard. Force position dot y, and so let's just double check as this. Let's just try it. No need to double check, whatever. We could also divide this by the size so that we get that same kind of functionality that we had before with like the lighter particles being affected more. And then finally, let's go ahead and say, okay, velocity.x plus equals y force and velocity.y. Velocity.y plus equals y force, and then this should be x force. Holy, okay, so they just got blasted. So this is way too strong. So let's try changing these to like 0.001 or something like that. Still getting kind of blasted. Interesting. Curious to make these negative. What if it's like a sucking force instead of or like a pulling force instead of a pushing force? It's kind of unclear what this did, to be honest, because I did it a bit too fast and loose. So let's just like do this correctly real quick. So what we'll do is we'll say, okay, let's actually, I'm going to go back to this vector 2 strategy I was thinking about earlier, and we'll say that vec2 is new vector 2, where the x component is going to be, I'm kind of trying to think, okay, do we want, so if we want it away, I think we want position.x minus point force position.x, and then same thing for y. Okay, great. And then from here we can say, okay, what is the magnitude of this vector? So let's check on the docs here for how to do that. Magnitude or size or length. What do they call this thing? Length. Does this have like a dot length property? Dot clamp length, huh? Dot set length? No, we want get length. What magnitude? Does it have a mag? Distance? I mean, we can do distance 200. That's an option. I was kind of hoping there'd be some better helper properties. I mean, they probably exist in here, and I'm just kind of not seeing them. Okay, let's just do this with actual math instead of relying on this. And so we'll say, okay, we know that the distance between the particle and the point force position is like Manhattan formula or whatever, math dot square root of x dx squared. So this is going to be position dot x minus point force position dot x squared plus same thing for y. Okay, so this is the distance between these two particles, the point force position, and so then we'll say that the and let's make a force strength for this thing. So point. We'll just call it point force. So the force is going to be equal to. Well, we're going to want to reduce the force if it is farther away. So we'll say point force, and so if this thing is a big number, then we'll probably want to divide by it. So if it's further away, the force should be smaller. So divide by distance, and maybe also divide by size afterwards. We could also say distance times size. This might be a little more clear. So we're going to reduce that force if the particle is further away from the point, and then finally we need to say, okay, what direction is this force going in, and let's, I mean, we have a lot of options. It just kind of depends what we want to do. You know, if we want it to be a pushing force where it just pushes things away from it, then we could just like calculate what, what the direction directly away from this is. An easier way that might also cause like a different result would be to just say, hey, just, if things are near it, make them go up, like an updraft or something like that. So let's try that, or we could do a downdraft. But yeah, we'll just say that this force is going to be or we can make it a right draft. We have so many options. Or a left draft. Um, let's make it a down draft. So we'll say that velocity dot y minus equals force. That should be it. Um, so is this actually doing anything is the question. Let's try making it stronger. Oh yeah, so yeah, you could clearly see that that had some influence. So you can see there's kind of like a downdraft right here at 0, 0. Yeah, that's cool. I think that actually does add kind of a more random wind-like element to it. That's really nice. So, oh, and I realize that my screen is kind of blocking this, but I think you get the point. So anyways, that is it. That is our wind snow particles. I thought this was pretty cool. So with this, instanced mesh we were using, you can render a ton of particles. Let's just push this thing to the limit. Look at that, 10,000 particles, no problem. 100,000? Look at that, amazing. Um, so I hope you enjoyed this tutorial. If you want to see anything in the future, feel free to request it. And yeah, catch you in the next video.